All right, we're going to go ahead and get started. I'd like to start off by welcoming you all to the MindWare training webinar on the EDA analysis software. My name is Eric Morgan, and I'm a software engineer at MindWare Technologies, and I'm going to be your host today. So we'll start off by going over what's on the agenda for the day. The webinar is going to be broken up into two main components, a walkthrough and a question and answer session, each of which will last around 30 minutes. Throughout the walkthrough, we're going to talk a little bit about what EDA is, what it is we're measuring, and what we're looking for when we analyze EDA. We're then going to open up the EDA analysis application, and we're going to go through some of the basic configuration steps involved in looking at EDA. We're going to look at the analysis screen, everything that's on that screen, the statistics that we're deriving. We're going to look at some editing techniques of inserting and deleting peaks and troughs and moving them around. Then we're going to look at how to write that data that we've analyzed out to Excel, and we're going to load a previously edited data file because it's not necessarily as simple as opening the file that you already edited. So throughout this presentation, feel free to ask any questions that you'd like as they come up. We will be answering those at the end during the Q&A session. We won't be answering them throughout the walkthrough portion. So if you ask a question and it's not answered right away, don't worry. We've seen it, and we will get to it at the end. And you can actually access the questions log as part of the GoToWebinar interface using the screenshots shown here. So if it's not already expanded, go ahead and do that so that you can ask a question when one comes up. So what is EDA? EDA stands for electrodermal activity. And throughout history, simply due to the way the science has evolved, the different techniques that were used to acquire EDA, it's gained a number of names that are sort of used interchangeably in the publications. So you might have seen this labeled as EDR, electrodermal resistance, or GSC, galvanic skin conductance. Even us at MindWare occasionally refer to it as this, GSR. But really, they're all talking about the same type of measurement, and that is EDA, electrodermal activity. What we're measuring with EDA is a change in the electrical conductance of the skin, which is measured in microsiemens. And this change in conductance coincides with the activation of sweat glands. Typically, EDA is collected with 2 electrodes on the palm of the hand, but you can measure EDA several places on the body, the soles of the feet, the fingertips, but the palms of the hands are particularly good because of their high concentration of sweat glands. And studies have shown that EDA is a good indicator of sympathetic nervous system activation. So when we see changes in the electrical conductance of the skin, we can correlate that to changes in the sympathetic nervous system. So we can really gain insight into the emotional state of a subject following the presentation of some stimuli. And when we're analyzing EDA, we're looking at 2 main components of the signal. We're looking at the tonic component, which is sort of the baseline EDA level, and we're also looking at the phasic component in these responses, or SCRs. And a skin conductance response is just a change in the signal that increases a certain level or amplitude following a stimuli. And it could happen from a stimuli that you know about or a stimuli that maybe you weren't controlling for. And I'm going to show you in the EDA analysis application some settings that pertain to how these skin conductance responses are defined, which is ultimately going to be written out in your Excel file and used to determine what sort of response someone was having to a particular situation. So with that, I'm going to open the EDA application, and we're going to start looking at some of the basic configuration of the application. Okay, so with the EDA application open, I'm first going to go to the File menu and choose a file to analyze. I have 3 examples today, and I'm going to choose the first example to start with. Now, you may be familiar if you're using MindWare Mobile, or if you're using the new Biolab software, the file formats MWI and MWX. And those are the newest file formats that we write. And the MWI file is the file that you're going to open when you go to analyze your data. We also support the older .mw file format as well as the acknowledge file format. So the first thing that happens after we open our file is the application wants to know what channel is mapped to what signal. Because just because we labeled them well when we were acquiring them doesn't mean that that channel definitely contains that signal. So for EDA analysis, the most important signal to map is obviously EDA. And as I mentioned earlier, sometimes at MindWare we refer to it as GSC. So I'm going to come down here to the first subject and choose EDA as that channel. I'm also going to map my impedance channels because respiration can be used in the EDA application to help us with some artifact detection and editing. So I'm going to map those two channels and press OK. And now we're on our setup screen. So some of this I'm going to go through fairly quickly because it doesn't pertain directly to EDA. And the second tab is what we're really going to focus on. So this first tab, Events and Modes, defines how we're going to segment our data. Now, this is a little more important in EDA than it is in some other applications because when we're looking at SCRs, the skin conductance responses, we want to see if they're directly related to an event or a stimuli that was presented to our subject during our experiment. And in order to do that, we have to be analyzing in event mode so that the application uses those events to segment our data and then look and see if those SCRs correlate to those events. So for my first example, I'm going to be analyzing in event mode, and I'm going to be looking 10 seconds before each event and 20 seconds after each event. And if you have any questions on this, feel free to submit them to the questions log, and we'll have time to talk about it a little later in the Q&A portion. So I'm going to quickly move to the EDA calibration settings tab. So this is the tab where you're going to set up all of the parameters that are specifically about EDA analysis. The first setting we see here is actually grayed out because I'm using an MWI file. So what's nice about, and actually an MWI file from the MindWare Mobile. So what's nice about using the MindWare Mobile is it can scale the data automatically into the proper units for EDA, which is microsiemens. And so since I'm using a file that was acquired on a mobile, this setting is grayed out because it's already being done for us. If you were using a Bionex module like our impedance module and you're collecting EDA that way, then we would see this microsiemens per volt filled in, and that's going to be equal to the gain that you used to acquire your data, because we want to divide that gain out and get back to the raw microsiemens. And if you're using something like an acknowledge file or some other third-party file that you imported into MindWare, we might not know that information at all, and you would have to tell the application. So in that case, you would then enter your own scaling factor of how to get your data from volts to the microsiemen value. The next row is all about those SCRs. So back on our slideshow here, we see that there's a latency associated with an SCR. So after the presentation of a stimulus, there's some time period during which no response will be seen, and then skin conductance response will occur. That's because skin conductance is a very slow-moving signal, and it takes a little longer to show reactivity. So there's a latency component, and then there's an amplitude component. There's a change in the amplitude of the signal that we want to use to consider something an SCR. And back in our application, we see this microsiemens threshold, which is that amplitude. So what amplitude change do we want to see before we consider something a skin conductance response? And generally in the literature, the the default value is 0.05 microsiemens. But it is editable. It's an editable parameter within the MindWare application. So you can change this to any value you'd like if you're only interested in responses that exceed a certain magnitude, for example. The next two are the latency window. So an ER SCR stands for event-related SCR. And we want to consider an SCR event-related if it starts within a certain latency following a stimuli. And by default, typically, these will occur between 1 and 3 seconds post-stimulus. So those are the default values here. But again, not everyone's in agreement about the time that it's appropriate to consider something event-related. So they are programmable, and you can change them to whatever you'd like. So these are in seconds. The next row, we see the calculation method. And this allows you to break up your segment into many smaller segments to get statistics about them, even though you're looking at it in a larger context. I'm going to leave it as an entire, but if anyone has any questions, or if we have time later in this webinar, we'll go back and we'll experiment with this a little bit, and I can show you what it does. The next setting we see is the resp signal to use. So remember, I mapped the impedance channels. And that's because we can derive the respiration signal from the impedance channels to use in conjunction with the EDA. And we're actually going to display that signal alongside the EDA signal, and we can use it to determine whether an SCR in the EDA is due to respiration, if it's due to artifact, or if it's truly a skin conductance response. I'm going to leave this at the Z0 channel, but if you had a rest belt or some other respiratory signal, you can choose that here. And finally, we have the rolling filter. So I recently wrote a blog article on the subject. If you go to support.mindwaretech.com, you can see that. But just to summarize, the rolling filter is a rolling average defined by the block size, which is in samples. So what we do is we take a certain number of points or samples on the EDA signal, and we compute the average of those points, and then we plot a new point on the resulting waveform. And we proceed through the entire EDA signal in that fashion. And it's really good for removing some high frequency or unwanted phasic content in the signal. But it's also very powerful and can very quickly alter the EDA morphology pretty significantly. So as with all filters, we don't want to use them at first. We want to use them when they are needed. So I'm going to turn it off, and I don't believe this first file needs the rolling filter, but we'll look at some later that the rolling filter really helps out with. Finally, we have our additional settings tab. Again, something I'm not going to touch on too much because it's sort of generic for all of the analysis applications that we have. But here's where you would map your videos if you had recorded videos along with your physiology. It's where you'll map your edit file, which we're definitely going to talk about later. And it's where you'll define where the Excel file is written, the output file. And so you can either just save it in this default location, as it always is, or you can specify where you want your results to be saved. So that's pretty much all there is to setting up the EDA application. And I'm going to press the green Analyze button and proceed to the analysis screen. Okay, so now we're on the analysis screen. And I'm going to talk a little bit about what we see here, what some of these different markers mean, the different statistics, and then we'll talk about editing a little bit. So the chart that's at the top is labeled phasic EDA, and this is your EDA signal. And it's marked with several color-coded complexes, which are the SCRs that have been identified in this segment. So an SCR consists of a trough followed by a peak and occasionally a half recovery time, or the point at which the EDA, or skin conductance, has dropped to less than half of whatever it took for the trough to the peak. And we can see those identified by a square at the trough, a circle at the peak, and an X for the half recovery. And we see that there are several skin conductance responses that have been identified in this segment. Below, we see our respiration. So this is our respiratory signal, and here it looks very clean, but if it weren't, we could possibly consider that artifact has resulted in both artifact in respiration and artifact in the EDA signal. But here it looks good. To the right, we see our SCR stats, which give detailed information about each of the skin conductance responses that have been identified in this segment. We see the time at which the event occurred, if it is based on an event. We see the name of the event that it's based on. And then the time and amplitude statistics about each of the points that make up the SCR. Now, all of this is going to be written out as well into the Excel output file. I'm going to go ahead and expand this so we can see everything a little better. So below the SCR stats table, we have a count of the total skin conductance responses that were found. We have the number of event-related skin conductance responses. So in this segment, we only found one that was event-related and 5 that were non-specific, or NS SCRs. These are skin conductance responses that have occurred that meet the criteria that we specified on the configuration page, but they aren't falling within that latency window, the 1 to 3 seconds post-stimulus, that we consider them, related to an event. And then we have Tonic SCL. So I mentioned earlier that we're looking at a couple different components of skin conductance. We're looking at the phasic and the tonic. Phasic being the SCRs, tonic being more of a general skin conductance level. And the way we're deriving tonic skin conductance level is we're taking the level of skin conductance but ignoring all of the time spent within an SCR, because that's where we're going to see our high amplitude changes and our settling. We don't want to include that in our baseline skin conductance level assessment. So we take all those out and we find the average level outside of those, and that's the tonic skin conductance level. And related, the tonic period is actually the amount of time that's spent outside of an SCR in any given segment. So in this particular segment, we're spending 12 seconds outside of an SCR and only about 8 seconds actually inside of an SCR. And finally, we have the mean skin conductance, which is taking an average skin conductance level of the entire signal, regardless of whether we're in a phasic component or not. So it's literally just an average of what you see on that chart. Okay, so I'm going to find a good segment to edit. Okay, so we'll look at this segment. So if we zoom into the second half here, you can see there's a pretty large skin conductance change here that's actually been split up into 2 skin conductance responses. But they aren't tied to any particular stimuli, so we can't really say that some stimuli occurred in the middle of the first one, thus causing the second one. So it's possible that this really isn't 2 skin conductance responses, but really a single large skin conductance response. And if you felt that way, it would be possible to do some editing to this signal to create that one large response as opposed to 2 separate ones. So I'm going to open the editor by pressing the Edit Peaks and Troughs button, and I'll expand this so we can see it well. And I'm going to want to delete this skin conductance response here. And so you always have to have a pair of trough and peak to constitute an SCR. So we want to make sure when we're editing our EDA signal in here that we're always leaving with a pair of those, with equal number troughs and peaks defined on our waveform. And if we don't, we will get an error, and I'll show you that as well. But for the time being, we're gonna really pay attention to the fact that we're deleting one trough and one peak always. We're never deleting just one or the other. So an easy way to make this a single response is to delete the peak of the previous response and the trough of the next response. So now we have the trough from response 1 and the peak from response 2, but we still have a peak and a trough pair. So if we press OK, we see that this smaller response in the middle, which may not be one, is removed, and now we have a single response which is much greater in magnitude and time. Another way to handle this sort of phasic activity that we don't really like is by using the rolling filter. So I'm going to press done here, and I'm not going to save my edits so that we can come back in and work with our raw data set. And I'm going to turn on our rolling filter. Now, if you read the blog, you can get some more specifics on why we do this, but we're going to start with our block size being equal to our sample rate. That's a good starting spot for how much data to take and average. And you really don't want to go any higher than 2 times your sample rate. The sample rate of this file is 500, so we're going to set it to 500. And I'm going to go back to that segment. And here, we can see that there is definitely a significant change in the morphology of this signal. It's become much more smooth, and that response that I edited out previously is not even there anymore. It's actually taken out that dip because that dip wasn't significant enough to make it through the averaging filter, the rolling filter. And so here we have just a single skin conductance response. So if you were analyzing with your rolling filter right off the bat, you wouldn't have even noticed that this was happening, which is why I definitely encourage you to analyze without filters before you analyze with filters so that you can understand the impact that they're having on your data. But here, that's sort of been taken care of for us. Now, I'm going to show you one other technique that you can use to do the same type of edit. So I'm going to turn off the rolling filter and return to that segment once again. And I'm going to open my editor, and instead of deleting the peak of the first skin conductance response and the trough of the second one, I'm going to delete the first response altogether. So now we don't have a response there. But we still want to capture this entire response, this lowest trough to this highest peak. We can go into our SCR point editor, which will actually allow us to move around these SCRs that are already defined, as opposed to defining new ones. So I'm going to drag this down to the trough and press OK. And now we've effectively achieved the same thing, but in a different way. And while the first method that I showed you would probably be the preferred method for doing the type of editing that we're doing, we do have the ability to just sort of make fine-tune adjustments of these skin conductance responses by using the SCR point editor instead of having to go in, inserting and deleting points. And finally, I'll show that just in case you were to delete a point and forget to delete its corresponding peak or trough, you will receive an error from the application saying that you have a peak-trough mismatch, which will give you an opportunity to press cancel, go back in, locate the place where you had missed inserting a point, and do so. If you continue, the application will guess as to which one you were trying to delete and just delete the other associated point, but I wouldn't recommend you letting it do that. I would actually recommend hitting cancel, figuring out where something might have gone wrong and adjusting it accordingly. Okay, so now that we've edited our data, we're going to want to write the statistics for a given segment out to a file. And that's going to be done by pressing the white write button at the top here. When I press that, it's going to ask us if we want to create a new Excel file or select an existing one. Most of the time you want to create a new one. Selecting an existing Excel file is only really useful if you were doing some editing and writing out some values to Excel, you had to close your application for whatever reason, and then came back to it later. But it's so quick and easy to write statistics to Excel that it's probably best just to do it in a single session. So I'm going to press Create New, which will launch Microsoft Excel, and it will fill in all of the statistics from this particular segment. On this first page, we're going to have general EDA stats, and on the second page, we're going to have all of our SCR stats, so all of the stats that were from that table on the analysis screen right here. And we would continue through our file, making edits, writing out segments, and when we're done, we'll press the red Done button, and it'll ask you to save your edit data. So this time I am going to save my edit data. In the EDA application, the type of file that's saved is a .ede file, and it's automatically going to be saved into an edit data folder, which is in the same directory as your raw data file. So I'm going to press OK, and it's going to take us back to the setup screen. Now, if I were to close the application and open my data file from scratch, but I want to use my edit data because I've done all these edits to it, the next step I have to take before I press the Analyze button is I need to go to this Additional Settings tab and check the Use Edited Data button, and then choose the edit data that I want to use when analyzing the data file I've selected. Now, the reason that this isn't done automatically is because edit files can only contain data for a single participant. This file that we're looking at is actually dyadic. It has 2 subjects in it. And each subject has to have its own edit file for use with it. And so I have an edit file now for my first subject. And if I were to go through and analyze my second subject by mapping their channels instead, I would actually have to create a new edit file and do my edits there. And then if I wanted to recall them, I would have to recall those edits. So that's the reason for this extra step. And if you are, using an edit file, definitely remember to do this. Okay, I'm going to open up another file briefly, sample 3, and I'm going to map my channels again as Z0, DZDT for respiration, my EDA channel, and I'm going to map an event channel. And again, I'm going to look at this data in event mode, and I'm going to look at 10 seconds before the event and 20 seconds after the event. And all my settings look good. I'll press Analyze. Okay, so this data looks pretty noisy. The first thing I would try here is I would try to apply my rolling filter. Again, I know this data is sampled at 500 samples a second, so I'm going to leave it at 500. And you can see the drastic change that it's made in the data. It's now smooth. We can see it a little better. We can see more clearly where the peaks and troughs are being marked. And so I'm going to go ahead and analyze this file like this. I'm going to look for an event that's going to produce an event-related skin conductance response. Okay, so here we can see that an event occurred at 300 seconds. And shortly thereafter, there's a pretty significant skin conductance response that's happened. And to the right, we see that that skin conductance response has been tagged as event-related because it started within that 1 to 3 second latency that we defined, and it meets the amplitude criteria that we specified as well. So we see that it's event-related, and it's related to the sync summary event 3, which is this event here. And we see there's another skin conductance response that happens shortly thereafter, but because it started after that latency window, we can't consider it related to that event. So it's not marked as such. It's marked as non-specific. So That's how these responses are marked, both event-related and non-specific. That's how they're shown in the SCR stats table, and that's how they'll appear in your Excel output file. Okay, so that ends the walkthrough portion of the webinar, and we're going to proceed to our question and answer portion. So I'm going to be monitoring the questions log, and we will get to any and all questions that you submit, so feel free to start submitting them, and we'll get back to you. Okay, we've got our first question of how can I tell if I'm recording good EDA data? So there's actually a really easy way to tell during acquisition if you're getting good EDA. And you should actually do this before you start your session. You should do this in the preview window. And that is a sniff test. So respiration and EDA are sort of interlocked in some very complex ways. And you can elicit a skin conductance response by taking a sniff or a sharp breath through the nose, and you'll see that response occur within that latency window of immediately following the sniff. You'll see that change. And so if you see that, then you're collecting good skin conductance, and you can go ahead and proceed. And if you're not, then you may want to check your electrodes, whether they're fresh or dry. You might want to check the connections to the system, your gain, things like that. Okay, I've got another question about why the half recovery time is -1. And so we're not always going to see a half recovery time. It could be that another skin conductance response has started immediately following the previous one, which hasn't given the signal time to level out, to return to baseline. And in which case, it's never going to drop to that half recovery point before we're into our next skin conductance response. So if we never observe a half recovery, then it's going to be marked as -1 in the output file. All right, we've got another question about how respiration relates to a skin conductance response. So when you see an increase in respiration, there's a corresponding increase in sweat, which is going to be an increase in skin conductance. So if you see in your resp channel an increase in breathing, then you can consider the resulting skin conductance changes to be caused by or related to that increase in respiration. You can also use respiration signal to determine whether there might be artifact occurring in your, or error occurring in your data acquisition. So if you see a section of respiration that's particularly noisy, and in that same portion of data you see a lot of skin conductance responses, those may be more due to motion artifact than actual emotional response. So that's one way in which you can use the respiratory signal to gain some more insight on what's going on in EDA. Okay, we've got another question related to the block size of the rolling filter. So I mentioned that a good point to start with your block size in the rolling filter is equal to the sample rate at which the data was collected. But how do we find that sample rate? How do we know what it is? So in the analysis applications, the sample rate is listed on the channel map screen. So if I go to File, Map Channels, this is the same screen that comes up when you open a file. You can see the sample frequency listed at the top. You can see the same value in Biolab if you open the file for viewing. So those are two main ways in which you can tell the sample frequency. And I mentioned also that there was a blog post on the subject, so I'll go ahead and show you that. If you go to our support site, which is support.mindwaretech.com, we have a number of support options and a lot of articles that will sort of help you through some of the most frequently asked questions about our applications. We also have a blog, and the blog is less specific training and more general conversations and topics about how to use certain features or how to, the science behind some of the analysis that we're doing. And the most recent article happened to be about the rolling filter, and we talk a little bit about, what does it mean, how is it represented mathematically, when would you want to use it, things like that. So definitely go check this out, and there are definitely a lot of resources there that are very useful. And I almost forgot, I had mentioned earlier that if we had time, we would talk a little bit about entire versus interval calculation methods. So I'll go ahead and speak to that now. As I mentioned earlier, the calculation method will allow you either to calculate skin conductance level over an entire segment or calculate it over smaller time intervals within a segment. So I'm going to change my calculation method to interval, and I'm going to set my interval period to 1 second, meaning that I'm going to calculate the skin conductance level every second by second skin conductance. But I'm still going to view my data in the same event mode. So I'm still going to look at 30 seconds worth of data, but I would like to know as well, how is this changing second by second? I'm going to press the Analyze button. I'm going to turn my rolling filter back on first because we definitely needed that with this file. And here we can see some additional cursors on the screen, these gray cursors. And these are defining the intervals. So every second, like we said, we want to calculate a new value. And our mean skin conductance statistic is not a single value, but rather an array of values, one of which, or each of which, representing the skin conductance level in a given interval. So we can scroll through here, looking at the skin conductance values for each second of data within this segment. All of this information is also written out to the Excel output file for use in your stats packages. So there's a question about the 10 seconds pre and 20 seconds post that I've been using for all of my examples, and whether or not that is a standard practice. It's not really, but it does give you a nice window into a little bit of data before the event to see what was happening then, and enough after the event to properly see where the event-related skin conductance response is occurring. So really, I mean, the latency setting is 1 to 3 seconds, and for event-related skin conductance responses, we expect to see them within that time period. So 20 seconds is even a lot if we're only interested in capturing that particular skin conductance response. Now, if we want to see sort of the trail off, see how the subject is affected, longer after that particular stimuli, then yeah, you can increase this post-event time to as much as you would like, whatever it is whatever time frame you're interested in viewing. If you want to see, up to the next stimuli, what's going on with the subject, you can increase the post-event time to that, and it would be perfectly acceptable to do so. Okay, I've got another question related to bringing in data from third-party systems. So there are a number of devices that can collect EDA, and some of them are in the form factor of a wristwatch or something to that nature, and they're output in various output file formats. Well, we do have a way of getting that data into the EDA application for analysis with SCRs and everything that we do here with our MindWare file. And that is by using the ASCII to MindWare converter. So that's available from the Tools menu in all of our applications, including Biolab. And you can go to Tools, ASCII to MindWare converter, and you would select a file that you want to convert. So part of the criteria for being able to bring a file in is that it needs to be text-based, and it needs to be in delimited columns of some nature, so a tab delimited file, a comma delimited file. But as long as there's some separating character between channels of data in the file that you want to bring in, you can pretty much import it. And let me see if I can find an example here to show you. All right, so I think I've got a file, and I'm going to attempt to bring this into the MindWare application. So I'm going to press that file open, and I'm going to go to my data folder and grab this .csv file here from the Empatica device. Press convert, and it's going to open up our ASCII to MindWare converter. And some of the information you need to know about your file in order to bring it in properly is the sample rate at which it was collected, whether it's being stored in volts or counts, and what character is being used to separate the data channels. In this particular file, because it's a CSV, we know it's a comma. And just from knowing how the Empatica file is stored, I know that this 4 here means that the sample rate is 4. This is going to be different for every device, so it's important when you're doing this to get as much information about how the data is stored as possible so that it makes bringing the data in as easy as possible. If not, most of this is defined in manuals or something that's provided by the company that makes the product. And we're going to adjust where our data starts, so we're going to offset past this header information. And then we're going to say that there's an EDA channel available. And it's that simple. So once we have it in this form, press OK. We save it as a MindWare file. It's converted because it was a very small file. And that's all there is to it. And now we can open it up in the application. So assuming that I did that right, because I'm sort of doing this on the fly, I'm going to turn off my rolling filter, open it up, and we have some semblance of EDA data. Probably needs to be modified a little bit, probably needs to be filtered, but that's generally how you would get the data into the application. Okay, we've got another question about events that are marked in a third-party program, such as null this observer. So there are a few different ways in which you can bring events into the analysis application. There's the event file, which is created automatically in Biolab if you're using an older version of Biolab. Or if you're using a version of Biolab that creates MWI files, those events are stored in the MWI file itself. So they'll automatically be populated on the events and modes page in this event list. If your events are being recorded as a digital event channel using a Bionex, then we have to map the event channel in the channel mapping screen, which I believe I did with one of these examples. So yeah, I mapped an event channel here, and we're going to detect the events from that event channel. We're going to detect the digital pulses and label them based on the values that they are, and then we can analyze based on those events. Or if you're using Observer, we actually partner with Nullthis, and we're able to import their event files natively. So you would basically, from Observer, export your events as a text file. And then up here in this event file path, you would specify your Observer event file, and those would come in and be displayed here the same way as the events that I've shown you today. So a few different ways we can get events in. But once you get them in, the analysis based on them all works the same way. So I've got a question about tonic skin conductance versus mean SCL. And it's sort of difficult to say, when you should use one or over the other. It depends very much on the context of where they're being used. But it's important to understand that, tonic is that baseline skin conductance level. So it's the level from which all these SCRs are occurring. And the mean SCL is taking into account all the SCRs that occur throughout your segment. So mean SCL is going to give you more of a picture of the reactions that are occurring during a given time period, whereas tonic is going to give you just sort of the general level that they were at that point in time. All right, so that concludes all the time we have for a webinar today. I'd like to thank you again for attending, and be on the lookout for future webinar offerings as they come up on our training website. Thanks, and have a great day.